you have discussed about the time slot with the other.
Yes, sir, we have floated a form and
Okay.
we'll
So
soon let you know about what we will prefer.
okay, so I am recording for today, but next time onward we will not have a tutorial class recorded. Okay, so those only uh, the tutorial will be live. Okay, all right. So can you see the whiteboard?
Yes, sir.
Yes, sir.
So problem number 1, let me just copy here. Okay, so can you see the statement here?
Yes, sir.
All right. So what is been given is what is been given in the problem is a wall has 2 layers of insulation. So there is a wall. Okay. So let's say this is the wall. And this wall has 2 layers of insulation. Okay. So in the first case, what is been given is the thickness is same. So this, let's assume that this thickness is L and this thickness is also L. Okay. Again, what is been given is thermal conductivity is K1 here and here it is K2. Thermal conductivity of layer 1 is twice that of the layer 2. So this is equals to twice K2. Okay. And okay, now in this particular problem, what is been given is we have to find out uh, how much more thicker should layer 2 be if the heat flow is reduced by 20% and the total wall thickness and driving force remain unchanged. So what we are trying to say here is if I change this thickness, if I change the thickness of layer 2, keeping this total length same as 2L, in that case, what by what fraction we should change the thickness of layer 2 in order to reduce the heat flow by 20%. So in this case, let's first look at the rate of heat flow. So rate of heat flow Q in this case will be given by what? Delta T divided by K1A plus L by K2A. Isn't it? This is what the equation is. Correct. Again, we can write this equation as delta T divided by L divided by K1 is same as twice K2. So we can write that twice K2A plus L by K2A. This is, let's say, equation number 1. Now we wanted to reduce this Q by 20%. That means the new value of Q will be now this system we wanted to change a little bit. Maybe I'll just draw another figure. Now I wanted to change this. I wanted to change this figure slightly. So now this distance is, let's say, x. So what will be this distance? This width will be
12 minus
2l minus x, correct, 2l minus x. So I wanted to find out what will be the new thickness of the second layer, which will reduce the rate of heat transfer by 20%. So with this, the Q new is going to be what? 0.8 Q, isn't it? Because it is reducing by 20%. Correct. And this will be given by what? The equation in this case is going to be again delta T divided by x by K1A plus twice L minus x by K2A. This again we can rearrange as delta T divided by.
Excuse me, sir.
Yes, please go ahead.
Sir, will the area not change?
Why
Because,
area will change?
sir, because we are changing the length of the
So which area we
materials.
take? Which area we take when we are looking at the heat transfer?
Area of cross section.
So cross section is what?
Sir, if we change the see, the volume should remain constant for that material. So if we are changing its length, the area should also change. Because earlier the volume was AL, so now it will be A1X.
I understood your question. I understood your question, but I am giving you maybe complete picture. You will able to look at it now. What is cross sectional area? Cross sectional area is this area.
Yes, sir.
So is this area going to change if I move this length?
Yes, sir. If we compress the first material, see earlier the length
So
was
we are
L.
not
Now
saying
if
the
we
compress. We are not saying the compress. What we are saying is this length of the block will be changed. So the cross sectional area is going to change.
so, sir, volume of that material will also change then.
So volume we are not asking. We are saying only the cross sectional area, isn't it? Cross sectional area is going to remain the same. What is the question? Question is saying compressed. Is it saying
Sir,
compressed?
Sir, it is saying that what new length of that material too should
What
be
new?
there.
So this new length is going to change. Na? This new length is going to change, but this cross sectional area is still going to be the same as A.
Sir, for separate materials, earlier the volume of material 1 was A into L, and volume of material 2 was also A into L. But now the volume of material 1 will be.
Where is the question of volume here, Raman? I am not able to see.
Sir, I wanted to say that are we changing the amount of material also? Because it is
In the
not
problem, see, in the problem, what is being mentioned is the length, thickness of the block is going to change, isn't it? Thickness of the block is going to change. Earlier, its thickness was L. Now I wanted to change that to some other value, but the total thickness of the complete block, composite block, that is still same as 2L. So one material is the thickness of one material is reduced, but at the same time, second material is increased by the same amount of length. We are not saying anything about volume. Still not clear?
So the total volume will remain the same because when we
Why
add both of
we are
them.
going in a volume? I'm still not able to understand why you are going there in the volume.
Sir, I just wanted to know that since it is not written that we are also adding some amount of material or we are removing some amount of material. It is just written that we are keeping the same block and we are just changing the length. So, sir, if we just change the length of the materials, then even if the total volume remains the same, but the volume
No,
of
no, we are
each.
not at all, not at all. We are not saying that the volume of that block is going to remain same. No, we are saying that the volume of this complete structure is going to be the same. Okay, we are not saying you have taken it in a you have, I think, tried to extrapolate in a different way. You are kind of saying that length we are reducing, that means this volume, because since the volume of this block 1 is going to be same. No, we are not saying that, not at all.
Okay, okay, sir.
I understood now. So you are saying, see, this is, let's say, block 1, this is, let's say, block 1, this is block 2, and if I go up here, this is block 1. Just a minute. This is block 1 and this is block 2. We are not saying that the volume of block 1 is going to remain the same or volume of the block 2 is going to remain the same. No, we are not saying. We are saying that this complete block volume, total 1 and 2, is going to remain the same. But this mid in between interface is there, that interface is going to move. So that means thickness of one block is going to reduce, but at the same time, the same amount of thickness will be added in the second block. That is what we are saying.
Okay, okay.
Okay, so initially we started with the same thickness equals to L and L. That's why the total length of this block, total thickness of this block was 2L. But in the second case, we are saying that we need to move this interface in such a way that there will be a reduction of 20% in Q. So that means the new Q value is going to be 0.8, isn't it? And the thickness of the block 1 is going to be just, let's say, X. Then the thickness of the second block is going to be 2L minus X, because total thickness of both the blocks is same, L, twice L. Is it okay now? Is it okay? Hello?
Yes.
So now this is again going to be 2K2A plus 2L minus X K2A. This is equation number 2. Now if I divide equation number 2 by 1, what we are going to get? If we divide equation number 2 by 1, in that case, what we are going to get is 0.8. Okay, this delta T, this driving force remains the same. That is what is been given in the problem statement, isn't it? So delta T is same. So temperature difference is going to remain the same. In that case, what we will be left with is L by 2K2 L by K2 divided by X by 2K2 plus 2L minus X by K2. Are you all agree with me? Are you all agree with me?
Yes, sir.
So how X and L will be related? Now here in this case, everything you can, rearrange and find out how L and X is related. Find out. This K2 also we can take common, and this will also get cancelled out. So find out how L and X is related.
Sir, X is equal to L by 4, I think.
Yes, yes. Yes. So are you all getting the same? X will be.
Yes, sir.
X will
Yes,
be
sir.
obtained
Yes,
as 0.25 L. So what information this particular answer is giving me? This particular answer, this particular equation is going to give me the information that if I reduce the thickness of block by 75% and increase the thickness of second block by 75%, then my heat transfer is going to reduce by 20%. Do you all agree?
Yes, sir.
Yes, sir.
Yes, sir.
The thickness of layer 1 should be reduced by 75%. And the thickness of layer 2 should be increased by 50%. Correct. This is the answer of first part. Now in part 2, what is been asked? In part B, what is been asked? In part B, it is been given that, let's say, if the layer 1 is replaced by, completely replaced by the material of layer 2, in that case, how much will be the total reduction? Isn't it? That is what the question is. Do you all agree? Hello? Hello?
Yes, sir.
Yes, sir.
In part B, what is being asked is, if I replace this block 1 completely by the material of block 2, that means both block 1 and block 2 are made up of same material. In that case, how much will be the reduction in rate of heat transfer? So let's say new Q value is Q dash. For this case, if block 1 is replaced by material of block 2, let's say, in that case, this new Q dash will be given by what? Delta T divided by, now what is the thickness of both the blocks? 2L divided by thermal conductivity of both the blocks now will be K2
K2.
and area, isn't it? So let's say this is equation number 3. If I compare this equation number 3 with the original equation, if I divide Q dash by Q, what I'm going to get? If I divide Q dash by Q, what I'm going to get? L by 2K2A plus L by K2A. This is from the equation number 1 divided by 2L by K2A. So what we are going to get? L by 2 plus L divided by 2L, isn't it? Correct? Yes or no?
Yes, sir.
So what we get from this? 2L plus 1L, that will be 3L by 2, and that 2 comes here.
So 3 by 4.
3 by 4.
3 by 4. Yes. So that means from this equation, what we are going to get is Q dash will be 3 by 4 Q. Isn't it? So that means Q will be reduced by
25%.
25%. Do you all agree? Do you all agree?
Yes, sir.
Yes, sir.
So this is the answer for part B. Now let's look at question number 2. Okay. So question number 2, again I am copying for you guys, and I will give you some time So that is easy. Both the questions are just Mickey Mouse type of simple questions because this is the first tutorial. As we will progress, you will see that the level of the questions are going to become more and more difficult.
Sir, can you up the screen so that I can see the solution of second B part?
What happened?
Sir, please scroll up. Sir, can you scroll up?
I will scroll up. From here?
No, sir, from B part.
Is it clear to everyone? Can you start solving the part second question?
Yes, sir.
Yes, sir.
Solve the second question. This is already here. So is the problem clear to everyone? So in the second problem, what is been given is there is a hot chamber. A hot chamber has an 8 centimeter thick inner layer of fire brick. Thermal conductivity is given 1.04 watt per meter degree Celsius, and a 30 centimeter outer layer of ordinary brick with the thermal conductivity of 0.69 watt per meter degree Celsius. The inside and outside surface temperatures of the composite wall are given as 400 degrees Celsius and 75 degrees Celsius respectively. Considering that the outer surface temperature is too high, it is decided to apply a 5 centimeter thick layer of plaster on the outer surface. On doing this, the outer skin temperature is reduced to 60 degrees Celsius and the rate of heat loss is decreased by 250 watt per meter square of the inner wall. Calculate the thermal.
Sir, I have a doubt in this question. Like it is given that the outer surface temperature is too high. How can the outer surface temperature be too high? Because it is a hot chamber. So in a hot chamber, the inside surface temperature should be too high, na? How could it be that the outer surface temperature is too high by logic?
Okay, so outer surface temperature initially was given as 70 Celsius. 75 is also very high. That is what it is said. Okay, is it clear now? This outside.
Okay. Yes, got it. I was thinking that 400. Okay.
Okay, so now, so what is been given is, let me just draw a figure again so that you will appreciate what I'm trying to say. So again, we have a composite block here. Now this temperature here is 400 degrees Celsius, 400 degrees Celsius. Okay, here the temperature is 75 degrees Celsius initially. Okay, so now what we are saying is thermal conductivity, and this is the fire brick. This is fire brick. And this is ordinary brick. Ordinary brick. Thermal conductivity K1 is given as 1.04 and here K2 is given as 0.69. 0.69. Thickness is given. Thickness, this is 8 centimeter thick, whereas this another wall is 13 centimeters thick. Okay. So initial condition is this. Initial condition is given is this. With this initial condition, the Q by A is given by, Q by A will be given by what? K into, so delta T divided by
KL.
L1 by K1 plus L2 by K2. Correct? So delta T in this case is 400 minus 75 divided by L1 is L1 in this case is 8 centimeter. So that becomes 0.08 divided by 1.04. That is the thermal conductivity. L2 is 13 centimeter. So 0.13 divided by 0.69. 0.69. So what we get from this is, what is the value you are getting from this? Calculate. Hello.
Sir, approx 1224.894.
So approximately we get 1225 watt per meter square.
Yes.
Okay, this is what we are getting. So this is the initial condition. Now what is being given in the second part? In the second new condition is, what we are saying is this 75 degrees Celsius temperature is, let's say, a too high outside temperature. So what we are doing is we are putting a plaster here. We are putting a plaster of 5 centimeter. So there we are putting a plaster means we are adding another layer of a plaster here with a thickness of 5 centimeter. and that has reduced the temperature from 75 degrees Celsius to 60 degrees Celsius. Okay. Also, the rate of heat transfer is reduced by 250 watt per meter square. So what will be the thermal conductivity of the plaster layer? That is what the question is. So let me again draw this figure again. So what we are saying is we had this first layer of we had this layer of, let's say this thickness was 8 centimeter. This we had 13 centimeter, and the third layer again we have added as 5 centimeter. Okay, this is fire brick. This is fire brick, ordinary brick, and this plaster layer. Correct. By adding this additional plaster layer, the outer temperature is now 60 degrees Celsius. And this temperature is again 400 degrees Celsius. And Q by A nu is reduced by 250. So earlier we had 1225 minus 250. How much is this number? 975 watt per meter square. Isn't it? So new Q by A is this. Correct. What is the K3? With this change, what is K3 value that we have to calculate? This is the question. Correct. So now again we can write down the equation here. So Q nu by A will be given by what? Delta T nu divided by L1 by K1
plus L2 by K2
L2 by K2 plus L3 by K3. Now delta T nu is what? 400 minus 60. Isn't it? Remember earlier it was 400 minus 75. Correct. Divided by L1 is 0.08 divided by 1.04 plus L2 is 0.13 divided by 0.69 and L3 is 5 centimeters, so that is 0.05 divided by K3, isn't it? And this Q nu by A is given by what? 975. So in this equation the only unknown is K3. Calculate the value of K3. Calculate the value of K3.
Excuse me, sir.
Please go ahead.
Sir, why cannot we also find it like equating the heat flow across the slab 3 and after insertion of slab 3 means like we know the temperature of junction is 75 degrees Celsius, and if we
No, that's not correct. Very good observation. That's not correct. Why? If you add another layer, your capital Q is going to change. So
yes, sir, I'm adding after that.
So don't anticipate that the boundary temperature of layer 2 and layer 3 will be 75. Don't anticipate that.
Okay.
Okay, you will get a different temperature. In fact, you calculate based on this.
Yes, sir, I calculated and got different answer.
You will get a different temperature. So that you have to keep in mind. It's not 75 in that case because your Q got changed.
Yes, sir, got it.
But sir, Q by A will remain same na at the interface. At the interface, Q by A will remain same.
But your Q itself is changing. That's what I'm saying. A is constant, but Q is going to change. So what is the value? Anyone?
Sir, it's coming out to be approx 0.6.
0.6.
0.6, correct. 0.6 watt per meter degree Celsius. This is what is going to be the answer. Is it clear to everyone?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. So is there any question related to the class which we have done today and earlier?
Sir, I have doubt at like in the question that at the interface, why not the temperatures would be the same?
The temperature is not going to be the same because your Q, capital Q, is going to change. Because now your capital Q will be based on all three resistances. Okay. It's not only based on the resistance of the layer 1 and layer 2, but also it is with respect to all three layers, all three resistances. Is it okay, Achintya? Not clear?
Sir, can you explain it mathematically?
So that is what we have done in the class, if you remember. Okay, I'll explain one more time. Just wait. Okay, so in this case, in the same case, what will be the equation? What will be the, just a minute. What will be the equation? We will have this equation. Q by A, Q by, this will be Q nu by A will be given as delta T nu R1 plus R2 plus R3. Okay, correct. And in earlier case, you had Q by A is given as delta T divided by R1 plus R2. R1 plus R2. Okay, and therefore your this individual, remember in this case delta T is given by what? T1 minus T dash, T1 minus T dash plus T dash minus T double dash, sorry, yes, plus T double dash minus T2, correct. Now here this T2, and in this case this T2 is new. T2 is new, correct. And therefore this T dash and T double dash both are going to be different. Also in this case delta T is given by what? T1 minus T dash plus T dash minus T2. That's it. Only 2 will be added. Can you see? This will be delta T.
Yes, sir. Yes, sir. Yes, sir.
And here this will be delta T. Is there any more question? Neeraj Gandhi is there? Neeraj, are you there?
Yes, sir.
So you wrote something about that if there is a temperature gradient is, if the temperature difference is 0, then the heat is generated, something you have written. What I'm trying to say is when temperature difference is 0, but if there is a heat generated in the system, then there will be heat flow.
Okay, sir.
Okay, I will try
Yes.
to explain. Just wait. Try to explain. If I'm having this particular block, let's say, here temperature is T1, here temperature is, let's say, T1. Both are temperature T1 at temperature. Will there be a heat transfer if there is no generation? If there is no generation in the system, in that case, your temperature profile is going to be this, isn't it?
Yes, sir.
Your temperature is going to be same as T1 everywhere inside. But let's say if there is a generation, if there is a generation, if there is no generation here, okay, and with generation, let's say if T1 is here and T2 is here, my temperature profile will not be like this, but instead my temperature profile will be like this. Did you get it? What I'm trying to say?
Yes, sir.
Okay, so your temperature profile will be like this because there is a generation taking place inside, so your temperature will not be constant throughout. So even though between these 2 points the temperature is same, but still there will be a heat transfer taking place. From this to here, the heat transfer will take place in this direction, and here the heat transfer will take place in another direction. Is it clear?
Yes, sir. Got it.
So what I'm trying to say is, whenever there is a generation, even though there is no temperature difference between the 2 points, but there could be a heat transfer because of gradient. So here you can see the gradient is not zero. Gradient is present. Gradient is zero at this point only. Other than this point, there is a gradient present. Correct? So therefore the heat transfer is going to be there. All right.
Yes, sir. Understood.
Is there any more question? Is there any question? If there is no question, let us stop here and see you all on Thursday. Okay. So ask all your friends to attend. This is the only one time I am recording this tutorial. We will not be recording the tutorial at all. Okay. Thank you, everyone.
Thank you, sir.
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 Thank you, sir.